Okay, so again, so we will have our take-home exam starting tomorrow. It will end on Tuesday. Okay. Don't forget to submit on Tuesday. Okay. Yeah. I will also remind you on that day. Okay, if you have a chance to submit that. And today we will finish all the contents. Okay. I did my best to cover most of the content that should be in the final. But it doesn't mean all the content will be they probably has more or a little bit more or less not in the content, not covered that I didn't mention in this class.
It would be on the final.
Probably, I don't know.
So things that you're not teaching us will be on the final.
Well, that's because that's a national ACS test. Okay, yeah. Maybe just a little bit. Okay. Because if I talk about that part, that's going to be 2 more classes. I mean, there's no way to talk about that in 2 more classes. Okay, yeah. If we have additional 1 more class, I probably will touch that. But today we probably not, because on Tuesday, I don't want to talk more new contents. Instead, we're going to work on our one of the practice, the final practice. Okay, yeah. So this is my plan. This is my plan. Okay, yeah. So I think yeah, pretty much this is what we're going to talk about. I'm going to grade everything by Tuesday. So I will grade everything by Tuesday. So you should have got your grades, everything except the final. Okay, and then if you have any questions, then you can let me know. Okay, yeah. Okay, so first of all, let's just review a little bit what we talked about last time. Okay, last time we talked about the most important thing is the geometry of the molecule. I mean, remember we have 4 or 5, well, based on different electron domain, we're going to have the different geometry. Okay, 2 electron domain, that's a linear. 3 electron domain, that's a trigonoplanar. 4 electron domain is tetrahedral. 5 electron domain is trigonobipyramidal. And 6 electron domain, that is the octahedral. Okay, and based on the difference, the number of the bonding domain and the number of the lone pairs, it gives you a different variation, right? And we also talk about the polarity. Okay, we talk about because the polarity is because we have a separation for the cation, for the positive charge and the negative charge. Okay, the polar and non-polar molecule is not talking about ionic compounds. It's majorly it just talking about molecular compounds, because ionic compounds are all polar. They have a positive charge and negative charge. They have extreme parts. But since the molecular compounds are non-charged atoms grouped together, and then but they are potentially they still have a positive charge, a partial positive and a partial negative on the molecule's end. So that's why they potentially got the polarity over there. So that's why we have some of the particle is a polar, some of the particle is non-polar. If you're just talking about a molecule with only single bond, then you just need to talk about the polarity of this bond. If this bond is non-polar, then there's a polar molecule. If this bond is non-polar, then that's a non-polar molecule. That makes sense, right? But if you're talking about the molecule, I mean more than one bond, then you just need to looking at the geometry of the molecules, right? I already listed the here. You probably didn't write. Then you can based on the table, you can write the polarity of those molecules. If we have a trigonoplanar this structure, and most of the cases, if there's no lone pairs, most of the case, the molecule are nonpolar molecule. If there's no lone pairs, most of the case is a nonpolar molecule. But if you see, so that's why is it trigonoplanar, the structure is nonpolar. Tetrahedral, the structure is nonpolar. And trigonobipyramidal is also nonpolar. And the octahedral structure also a nonpolar. Okay, so when we talk about this, they have under the condition, which is all the molecule, all the side atoms are the same, which is over here, you see, if we talk about octahedral, all the side atoms are the white atoms, then that's going to be definitely a nonpolar molecule. But if you change one of these to another particles like this, then definitely this is not a nonpolar, right? Because I mean, one of this is different. How come it can balance the whole electron? I mean, it doesn't. It can't. So that's why if you have the different molecule, then that's gonna be a polar bond. Okay, yeah. And then if this molecule has the electron, has a number of lone pairs, then there's only just two options. You see, there's this one has a lone pair, and the lone pair, and also lone pairs over here. There's only two exceptions. One exception is if this guy has a 5 electron domain, but has a 3 lone pairs, this guy is still a nonpolar molecule. That's because the 3 electrons in the middle is like this. They have a 3 electron domain. 3 electron domain. One is here, one is here, and one is here. So these 3 of those electron domain cancel to each other. So make the molecule is a perfectly linear structure. So that's why this guy is a nonpolar molecule. This is one of the exceptions. Another exception is if the 6 electron domain, they lose 2, become like this. Then one lone pair is over here, one lone pair is over here. Then those 2 lone pairs is kind of like a pushing equally to the middle of the 4 of those. So generally also make it nonpolar. Okay, so that's why there's only those 2 exceptions. The rest of others, if they have the lone pairs, those are all polar molecules. Okay, yeah. So generally, this is what we are talking about. Okay, this is what we talk about. So determining the geometry of the molecule is very essential. You can based on that to determine whether this molecule is polar or non-polar. Okay, yeah, so one more thing I need to mention, which is over here. If you're looking at the molecule, and you're trying to determine the geometry of the molecule, it's not just looking at their formulas. You see, we have 3 of those molecules, you see? Those all have 4 side atoms. But the geometry of those 3 molecules are completely different. So to determine the geometry of the molecule, not just looking at the side atoms. Meanwhile, you need to draw the Lewis structure. That is the most important thing. Draw the Lewis structure and see how many electron domain it has, how many bonding, how many lone pairs. And then you base on the number of lone pairs, bondings, and then to determine the geometry. You see, the first structure, SF4, this guy has 34 electrons. And then if you draw the Lewis structure, you see there's a 5 electron domain for the central atom. In other words, this guy has a 5 electron domain, but they only have 4 bonds and 1 lone pair. So that's why they give us one of the structure is called a seesaw. It's a seesaw structure like this. Okay, this guy only there's a 4 bonds and 1 lone pair. So give us a seesaw structure. Okay, so and then if you're looking at the second one, xenon tetrafluoride, xenon, then you will see this guy has 36 electrons. So they have 4 bonds, but they have 2 extra lone pairs in the central atom. In other words, this guy is not a 5 electron domain anymore. So the geometry is not this one. The geometry becomes something like that, right? And then there have a 2 electron domain, 2 lone pairs, just like this, right? 1 lone pair here, 1 lone pair here. Then make this structure as the square planar instead of like this, right? So this is 2D and this is 3D. And if you're looking at the last one, they have a 32 for the electrons, and then make this carbon only 4 electron domain. So they give us the structure of this molecule as a tetrahedral. Instead of it becomes a tetrahedral. It's something like that, right? So this is a tetrahedral. So that's why you cannot just based on the formula to determine the geometry of the molecule. You have to draw the Lewis structure and determine how many electron domain around the central atom, and then you based on that to determine the geometry. Are you clear? This is very important. Okay, so to determine the geometry of those, you have to draw the Lewis structure. That's very important. Okay, yeah. So this is pretty much what we talked about last time, and today we're going to talk about one more topic, which is pretty related to what we talk about. It's called hybridization. To talk about hybridization, okay, there's an easy way or there's a more advanced way to talk about hybridization. The more easy way is just you're gonna remember it. Okay, the hybridization, there are only just several different ways to do the hybridization. But I would like to talk about a little bit more conceptual. Okay, why we have those hybridization. Okay, and then it will help you to understand. So for this, then we need to talk a little bit. It's called the MO theory. It's called the MO theory, and the MO is represents molecular orbital theory. I don't want to talk about this too much because if we talk more, this is another 2-class topic. Okay, so that's just I'm just touching about this. So MO theory, generally what they are talking about, they're talking about the molecule. So we talk about hydrogen and hydrogen, they're sharing the electron, right? But how come they're sharing the electron? The MO theory talking about, okay, so the hydrogen has an s orbital, right? They have a nuclear, then they have an s orbital, and s orbital is a ball, right? This is a 1s orbital. And another hydrogen also has a ball. This is also 1s orbital. When they combine together, then they have an overlap. And this overlap part, those 1s, this is also 1s. Two 1s combine overlap together, and this is overlap area is what we call a bond. So generally, this is the essential part for the MO theory. We talk about if we have the orbital overlap, and then the bond is formed. It's because of the overlap. Okay, so that is why you say hydrogen. If you write the electron diagram, you know this is a 1s orbital, this is 1s, and this is hydrogen. This is also hydrogen. And hydrogen, this here has a 1 electron, and this hydrogen also has another electron. So those 2 electrons, they're paired together, then they are building a bond, right? In another word, if you want to build a bond, you have to have a single unpaired electron in the orbital. If you don't have the single paired electron, then you're not going to have a bonding. That makes sense, right? Okay, so that is why if we talk about, so this one, the hydrogen and hydrogen has a s and s orbital overlap. So, right, so s and s orbital can overlap, but also the s and p orbital can also overlap. One of the example is just hydrogen and the fluorine, right? We know we have the HF, the molecule. So how this guy bonds? Hydrogen has a 1s orbital. This is 1s. They have a single electron. The f orbital, F also has the electron configuration for fluorine is 1s2, 2s2, and 2p5. So the electron diagram for the 2s or for the fluorine is something like that. This is a 1s, 2s, and a 2p, s, 2s, and 2p. You see, the reason the fluorine would like to bond because they have one of the lone pairs in the 2p orbitals. So they would like to pair another electron to making it stable, making those are fully occupied. So that's why they would like to pair another electron, and then hydrogen can offer one of the electrons, so those two can pair together. So in this case, this paired overlap, this is the s orbital, and this is p orbital. So that's why the s orbital and the p orbital can also overlap together. And this guy will all overlap together, and this is making another bond. This is another bond. It makes sense, right? So this is another bond. And if you're talking about the fluorine gas, right? Fluorine gas is what? Is a fluorine and fluorine together. So in another word, this guy is 1s, 2s, and 2p. This is also 1s, 2s, and 2p. 2p, 1s, 2s, and 2p. So you see, fluorine, this guy has a 1 unpaired electron. This guy also has a 1 unpaired electron. Since they have those unpaired electron, so they can pair together and making another bond. But this case is not a s orbital and p, and also not a ss. But right now, this is a 2 of the p orbital. They overlap together. And this is overlap together. That makes sense, right? So do you understand the example that I gave to you, right? So now you see the s orbital and p orbital, they can overlap. Okay, either is ss or sp or pp. So they can overlap together, especially the p and 2p orbitals. They head-to-head overlap, must be head-to-head. There's another option. It's a side by side, but that's another way. So listen to me. There's a head-to-head overlap, and we have those 3 different options. And this is all making a bond. And this kind of bond is called a sigma bond. So this kind of overlap is what we call the sigma bond. Maybe you heard the sigma bond before, okay? But you never know what is that, okay? So sigma bonds is the overlap between ss orbital, sp orbital, and pp orbital. Okay, so that is the sigma bonds. Okay, they are making a sigma bond. So in general, what we represent as in the sigma bonds is a single bonds. In the geometry, in the molecule, the sigma bond are all the the single bonds are all sigma bonds. Okay, all of those single bonds are all sigma bonds. Either is the SS orbital overlap or PP orbital or SNP. Are you clear? Okay, so this is making single bonds. But obviously, there's another bond. It's called the pi bond. And T and T. You see, this is a P and P. You see, this is a P orbital, and this is another P. So P and P overlap together. So this is generally what we can see. That's a sigma. And most of the case, if you see the molecule like this, you see, this guy has 4 single bonds, and each of those single bonds are counted as a sigma bond. So sigma bond are all single bonds are all sigma bonds. Okay. And then there's another type of bond. It's called a pi bond. A pi bond is making 2 different things. Pi bond. What is a pi bond? Pi bond is the 2 of the p orbital overlap together, but this overlap is not overlap like head-to-head overlap. Its overlap is side by side. How come it's side by side overlap? We have the 1 of the p orbital, right? And there's another p. So you see, this and this overlap together. This is what we call a pi bond. Okay, so P and P side by side overlap is called the pi bond. But the 2P head-to-head overlap is called a sigma bond. Okay, so this is very important. Please remember. Okay, please remember this. Okay, is a different. Okay, so where we can find the pi bond? The pi bond can only shows in double bonds and triple bonds. Can only shows in double bonds and triple bonds. So in general, if you have a double bond, double bonds, remember that's a 2 dash, right? They containing 1 sigma bond plus 1 pi bond. This is how we have for a double bond. So double bond containing 1 of the sigma bonds like this, which is 2p orbitals overlap, and some other bonds are sigma bonds. Okay, so this is what we see for a double bond. But for triple bonds,
So
T and P, but this is P and P orbital, which means if you have a p orbital and this p orbital has a single electrons, then they may have a chance to have a pi bond, but not always, because p can also overlap with s orbital to making a sigma bond. So if you have a multiple, we will talk about this. If you have a multiple single electron in the p orbital, and this single electron may have a chance to making a sigma bond, and also making has a chance to making a pi bond. Okay, so that's why sometimes you may have a triple bond, sometimes you have a double bond. Yeah. So triple bonds, what happens? Triple bonds. What? Yeah, it can only shows in the P. So triple bonds is containing 1 sigma, but they are plus 2 pi bonds. Okay, they can have 1 sigma and 2 pi bonds. So generally, this is how we count the number of those pi bond and sigma bonds. Okay, so generally, how the exam test, they probably give you one of the structure like this. Okay, so they give you one of the structure over here, and then they're asking you how many pi bond it has, how many sigma bond it has. Well, then just based on what we learned, okay, pi sigma bonds, all the single bonds are sigma bonds, and one pi, one double bonds containing one sigma and one pi. Okay, triple bonds containing one sigma and two pi's. So now you see we only have one double bonds, right? Nothing else, only just one double bonds. So that means we should only have a one pi bond. That makes sense, right? And then how many sigma do we have? Then you just need to count. Okay, 1, 2, 3, 4, 5, 6, and also in the double bonds, because one double bond containing one sigma and one pi. So now we have 1, 2, 3, 4, 5, 6, 7. So now we're having 7 pi bond, 7 sigma bond. That makes sense?
This is considered a double bond,
Yeah,
because it doesn't matter how many sigma bonds there are, but as long as there's one present. But it depends on the number of pi bonds are present, that determines whether it's gonna be a double or triple.
here we're talking about the question may ask you how many pi bonds and how many sigma bonds present in this molecule. Okay, and then just easily to count, okay, how many single bonds we have. The number of single bonds refer to number of the sigma bonds. And then one double bonds containing one sigma, one pi. Triple bonds containing one sigma, two pi's. And then just need to count, okay? So I have 1, 2, 3, 4, 5, 6. Now we have a single bond. That's called a six sigma, right? And we have a one double, and this one double containing one sigma and one pi. So that means we have a 7 sigma and one pi. It makes sense? Are you clear? Okay. So generally, this is how we calculate how many numbers of the pi and sigma and those things. Are you clear? Okay. So give you one more example. Most of the case is just to show the organic compounds for you. Okay. Those are all the organic compounds. Great. Okay, so that's a little bit complicated. I don't know, I just made up, but I mean, everything that should be true. Okay, so that should be correct. I mean, but I think this is accurate. Okay, so everything should follow the octet. Okay, yeah. So now, how many sigma do we have? How many pi do we have? Okay, how many pi and how many sigma? So how many pi, how many sigma? Okay, so now go ahead to count how many.
Yeah. Like the nurse one. It's four, then. Yeah. Oh, okay, then there are. No, that's on me, for sure. That's so bad. So. That's not bad.
Okay, so now what we're gonna count, we're doing this separately, right?
Yeah.
Because they have a double bonds and single bonds, okay? And then you, yeah, so then you can count, okay, so now how many single bonds do we have? Single bonds? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we have a 12 single bond. How many double do we have?
Oh.
We have a 1, 2, 3, and 4. So now we have a 4. Now you can just based on this to do the calculation, right? Sigma, 12 single bonds, that's all 12 sigma bonds. And the 4 double bonds means 4 sigma plus 4 pi. So now you're supposed has a 16 sigma and 4 pi. Are you clear about how to do this calculation? Okay, yeah. So just simply count how many single bonds have, how many double bonds, or even I didn't show the triple bonds, but if they have triple bonds, you can show 1 triple bonds has a 1 sigma 2 pi, not a 2 sigma 1 pi. Okay, 1 sigma 2 pi's. Okay, so that's why then you can based on this doing the calculation how many sigma they have, how many pi. Are you clear? Okay, not too hard, right? Yeah, as long as you see the molecule, you're supposed to figure out. That makes sense, right? Okay. All right, so this is generally essential part for the MO theory, and generally MO theory also write the graphs, but I'm not going to draw those graphs for you. The next part I would like to have is the topic is called the hybridization. I mean, when we draw the table, remember geometry, the table, we already talked about hybridization. And then let's see what is the hybridization. So hybridization is a part of the MO theory. It's a part of the still part of the MO theory. This is still MO theory. But generally, the hybridization is a patch. It's a pad. PAT6, how to spell patch, right? It's a patch for the MO theory. Okay, yeah. What that mean? So remember, when we talk about the MO theory, is talk about if in the electron orbitals, if you have a single electron over there, then the single electron will making a bond with another. That makes sense, right? But so that is why if we talk about oxygen has 8 valence electron, 8 electrons. So that's why they have 1 s2, 2 s2, and 2 p4. So that's why oxygen would like to be like this. So 1s, 2s, 2p, right? They have a 2p4. So that's why it's 1s, 2s, and 2p4. And then you see there's a 2 single electrons sitting in the oxygen. So that's why we talk about, that's why oxygen would like to either they want to making 2 single bonds, because the 2 single electron can making each of this as a sigma bonds. That makes sense, right? Or they can making double bonds, right? We also talk about they also making double bonds. In another word, one of the single electron making a sigma bond, the other one making a pi bond. making a pi bond, and then they are going to making a double bond. Does it make sense, right? So that's why this is perfect for oxygen. So this one, MO theory can explain that very clearly. But here is a but. The most important is a but. How to solve the carbon? If you're looking at the electron diagram, carbon has a 6 electron. This is a 1s2, 2s2, and a 2p2 for carbon. And then if you draw the electron diagram, then that's gonna be a different story. 1s, 2s, and a 2p. See, this is 1s and 2s and 2p. So now when we touch that part, that's gonna be it's hard for the scientists to explain. Again, MO theory talk about if you have one single electron, then the single electron can bind with the other to making a bond, right? Then you see how many electrons this guy has. They have a 2 single electron, right? In another word, the carbon can only making 2 bonds. But how can you explain the methane? How can you explain methane? I'm not going to explain that because methane has 4 bonds technically, right? So in a real life, the methane has 4 bonds. Where the 4 bonds come from? Does that mean the MO theory is collapsed? It's totally wrong. Yeah. So that's why I'm just saying. So that's why the people have to explain this. Yeah, and then they are making a patch. The hybridization is not a theory. It's just a patch for this. Okay. So they need to explain, okay, how come the carbon gonna have 4 single bonds?
It's all made up.
No, this is not made up.
It's just
This could be true. This could be true. Okay. So then what happens? Then the scientist, well, at least right now, this is makes sense. I mean, the scientists said, okay, so when we have this situation, the carbon now, first they're doing the promotion. They're doing the promotion. What does that mean? One of the electrons in the 2s orbital is jumped to the 2p. So when they are making a bond, so their promotion. Then they're making a promotion. There's 1s, 2s, and 2p. So they are making a 1s. So they're jump one of the electron from the 2s jump to the 2p position. Now it's good to expand. Now they are having 4 single electrons shows over here, right? But still, another question is, once you're making a methane over here, those are 4 bonds are identical, which means exactly the same. But if you talk about the 4s and the 2s and the 2p, we talk about those 2 orbitals has a different energy level. Then obviously those are not exactly the same. Does it make sense, right? They're not exactly the same. So that's why they have to do one more thing, which is called the hybridization. In other words, they hybridize the s orbital and the p orbital together. So that's why they call the hybridization. Okay. So now they said, okay, in this case, then we're going to have the s2s orbital and the 2p orbital all hybridized together to making 4 orbitals together. And this 4 orbitals is not called the 2p. It's also not called 2s. Instead, they call the hybridized orbital. They give it a spatial name. It's called the sp3. So this orbital, this is called the sp3. This orbital, whole orbital is called sp3. Then they still have the 1s over there. Then you will see, okay, so now in this case, the carbon is going to have 4 single electrons, and those 4 single electrons are identical, and then they are going to making the structure. They're making the hybridized. They can making 4 bonds with other things. That makes sense, right? So then the people says, okay, to be honest, at the very beginning, I really don't know. I mean, how come we have the s orbital shaped like this and the p orbitals shaped like this? And those two hybridized together, do you think what kind of shape it looks like? It's just one part is really big, and the other part is really small. So, sorry, I have a really terrible drawing. But generally, one is very big, another lobe is very small, and the electron is still in the same. So in the middle, the nucleus still in the middle. So this is what we call the hybridized orbitals. So this is the hybridized orbitals. Are you clear? Yes.
Is this like the sp3 one?
This is sp3. Okay, but most of the case, the hybridization orbital is or something like that. Okay, is or something like that. So this is and then this hybridization is what we call the sp3 hybridization. There are different kind of hybridization to explain the different way. And the best way I can help you to understand is if you want to see what kind of hybridization, you just need to see the central atom. Just like you count how many electron domain, then this is called how many electron domain around this central atom. This carbon has 4 bonds, which is 4 electron domain. Then that's going to be sp3 hybridization because S has one s orbital and 3 p orbitals. You see, because p has three of the p. So 1 s orbital, 3 p orbital hybridized together, making 4. So 4 electron domain will give you sp3 hybridization. This is the way that I remember. Okay, if this guy has a four electron domain, they give your sp3 hybridization. Totally give your 4 hybridized orbitals. Okay, then there's another situation. For example, if we have a carbon and this is a formaldehyde, this is a formaldehyde, and if you're looking at the central atom over here, the carbon, this guy, what happened? They are having 2 sigma bonds and 3 sigma bonds and 1 pi bonds, right? So 3 sigma bonds and 1 pi bonds. And by the way, the hybridized orbital can only making sigma bonds. Hybridized orbital can only make sigma bond. Can only make sigma bonds. Okay. So now, then the people will say, okay, how can we explain this? In this case, we have a 1, 2, 3. We have a 3 sigma bonds over here, and we have a 1 pi bond. Right. So in this case, then obviously it's not going to be sp3 hybridization because those in this case we can only making 4 sigma bonds. We're not going to making 1 pi and 3 sigma. So now the people say, okay, now in this case, we're going to have a hybridization in this way. So this is 1s. They are making another hybridization. It's called sp2 hybridization. Leave one of the 2p left over. Okay, so now this is another hybridization. Then in this case, the sp2 hybridization can offer 3 single electrons and paired with other single electron to making 3 bonds, 3 sigma bonds. And this p orbitals can paired with another p orbitals for making a pi bond. Then that's good to go. Yes.
I'm like a little confused because I thought you said that like the sp3 like hybridized orbital has like 4 like electrons and maybe that's sp2.
That's
sorry, I can't spell it. I'm sorry, I can't spell it.
Yeah, this is a sp2 hybridization
Sorry.
instead of sp3. Okay, So now this is sp2 hybridization instead of sp3. So that's why we can explain that, because this guy has a 3 sigma and 1 pi. So there's the only way in this case can explain that. And then to this one also, again, how to determine this one need a sp2 hybridization, you just need to look at the electron domain. This guy, central atom, has a 3 electron domain. So 3 electron domain give your sp2 hybridization, which is 1s and 2 of the p hybridized together give your 3 electron domain. Okay, so this is also compared to each other. And one more example is, okay, this guy also can have the situation like that. Okay, so this is carbon monoxide. How come this guy happens? Well, this guy, now you see, sorry. Well, let me write another. This is a method. Okay, so this guy also, for this guy has a 3. If you're looking at here, we have a 2 sigma bonds and 2 pi bonds over here. Then how come we make a 2 sigma and 2 pi? Well, then let's say, okay, now we have a 1s still there. Now instead of we're hybridize the 2 of the p or 3 of the p, we're hybridize only just 1 of the p over there. So now they're making a sp hybridization and leave 2 of the 2p left over, and this is 2p. Then you're going to have a 2 of the orbital single electron in the sp hybridization, and then those 2 will making 2 sigma bonds, and the leftover 2p orbitals can paired with another 2p to form the pi bonds. So that's why here we have a 2 sigma and 2 pi, and then making, you see, this is 1 sigma, this is another sigma, and the 2 of the pi, and the 2 pi is coming over here. So that's why we have this hybridization. Make sense? Okay, so this is, and then again, how can we easily to count what kind of hybridization for this carbon? Then just again, just looking at the paired electrons. How many electron domain? This guy only have a 2 electron domain. If this has 2 electron domain, then that's sp hybridization. Just one of the s and one of the p hybridized together give your 2 electron domain. That's easy way, right? So that's why if you want to count what kind of hybridization for this, you just need to count the electron domain. Number of electron domain and then hybridization. So if we have a 2 electron domain, then that's an sp hybridization. So remember, we always start from s. The s gonna combine with p first. Okay, so that's an sp. If we have 3 electron domain, then that's sp2. Okay, remember it didn't show s1, but because the s only just 1 orbital shows up there, so that's default. Then that's just sp2. But you gotta remember that's a S1 P2. So 1 plus 2, that's 3. Are you clear? And then if we have a 4 electron domain, then that's gonna be sp3 hybridization. That's sp3 hybridization. And then we have 2 more to go. Remember, based on the geometry, we have a 5 electron domain and a 6 electron domain, right? Then you can think about it. I didn't mention that, but you can think about. So now sp3 is already the maximum to hybridize the s orbital and the p orbital. Then we're going to hybridize the d orbital for the 5 electron domain. And then how many d we're gonna combine? Just 1. So that's just a sp3d hybridization. It makes sense, right? So if we have a 6 electron domain, which is the maximum, then that's going to be sp3d2 hybridization. Okay, So I hope in this way you can remember this easily, right? I mean, you just know where this hybridization comes from. It's a patch for the MO theory. That's it. Okay, yeah, because the people need to explain that. I mean, how come we have these things happens? Okay, so this is the hybridization. This is hybridization. The next one, I mean, if we have enough time, I'd like to talk about intermolecular force, but we don't have enough time to talk about intermolecular force. But I do have one thing I can explain that a little bit, intermolecular force. Okay, intermolecular force. Did you still remember last time we talked about the molecule? When we talk about the solid liquid stage and your adult stage, okay, right? About your life. So generally, it's the same thing. Intermolecular force is a force between molecules. So that's why it's called the intermolecular force, which is, for example, if we have a water molecule and between the water molecule, then they're having two of the water molecule, they're going to have an intermolecular force between the two molecules, not the force between the hydrogen and oxygen atoms. It's a force, invisible force between those two molecules. Are you clear? Okay. So that is what we call the intermolecular force. So different molecule will give you the different intermolecular force. Okay. One thing I would like to let you understand is the non-polar molecule usually has the really, really low intermolecular force. So non-polar molecule has much lower intermolecular force than the polar molecule. Non-polar molecule has a really low intermolecular force than the polar molecule. And how can we determine the intermolecular force? Usually, the intermolecular force is related to the boiling point and the melting point. So in another word, if you're try to compare the intermolecular force between the two molecules in just looking at their boiling point or melting point, then you will see. Okay, so that is why. Okay, so the common. Let's talk about the real life. The common non-polar molecule you can see is oxygen gas, nitrogen gas, hydrogen gas, fluorine gas. Chlorine, those are all gases. Okay, and bromine. But let's first talk about it. Bromine has a little bit heavier. Yeah, iodine is even heavier, so that's why. Okay, and then if you're looking this, those guys are all gases, right? Gases. Why we have a gas in the room temperature? That means the intermolecular force is so weak. Then you see, even just a little bit temperature, the room temperature don't have a really high energy, but even those low energy, you can boil it. So that's why you see, if we pour the liquid nitrogen, you pour those liquid out, it's starting boiling. And I mean, at once it started boiling. It's because this guy don't need. I mean, remember the intermolecular force is the force holding the two molecules, right? if the molecules has a really strong energy, then they try to break the force and fly away. So that's why they become a gas, right? Yeah. So that's why you say oxygen, nitrogen, hydrogen, fluorine, and chlorine. Those are all gases because the intermolecular force is so weak. Okay. Glue is in another way has a really strong intermolecular force. Okay. Yeah. Those molecules usually has a really big molecule. Okay. So they very connect to each other. Okay. So that's why this is a glue. So if you're a material scientist, you try to find a way to find a material for the glue. You have to find one that has a really big molecule. Usually is organic molecule, okay, and very complicated structure, and then that's going to be very good for a glue. Okay, yeah. But for those non-polar molecule, since this guy is so weak, so most of the case is liquid, and you see, compared to the water, water is a polar molecule, and water, what is boiling point for the water? 100 Celsius, right? But for the what is the boiling point for oxygen? That's going to be a negative 200 something, really low. Okay. Yeah.
Most stable and fast.
Yeah. So in another word, the boiling point is the molecule has enough energy to break the intermolecular force to let it free, to let it be free. Okay. Yeah. If I mean, we have to reach 100 Celsius, then those molecules has enough energy to let it free. Okay. Instead of the oxygen, the intermolecular force is really weak. So just a little bit energy, then they're free. Well, we cannot say this is gravity, but anyway, I mean, similar things, similar idea. That makes sense, right? So that is generally is the intermolecular force. And if you're talking about the ionic compound, they have an even higher intermolecular force. So have you ever seen any of the salt? Since the ionic compound, in most of the cases, is salt, right? Have you any see the ionic compounds? The salt is a liquid or gas in the room temperature? You never see it. Yeah. Most of those are solid. That's because the intermolecular force is too strong. It's even stronger than the polar molecule. Right? So room temperature, this temperature, I mean, they're not going to the intermolecular force is so strong to bond everything together. Okay. If you melt the salt, you have to reach to more than 1000 Celsius to let only just the salt, the table salt melt to become from solid to liquid. If it's become a gas, even temperature even higher. So you see, yeah, that is the difference between intermolecular force. Okay, yeah. So now we talk about the strength of the intermolecular force. Polar molecule usually has a really weak the intermolecular force. And the polar molecule is stronger. Then the ionic compound, ionic molecule or ionic compound usually has a much stronger intermolecular force than this. So from top to bottom is weak to strong. Okay, so this is pretty much I would like to talk for the intermolecular force. If you're joining to my M2 class, I will talk more about intermolecular force. I think this is a pretty interesting part. Okay, yeah, and the intermolecular force not just talking about. There's a lot of our lifetime experience actually is talking about intermolecular force. Okay, one of the example is the capillary. If you do the nursing, there's some of it's called a capillary. It's a capillary tube, which means a very small tube. If you do a blood test, you just like use a capillary tube and then put on the blood, then it will suck inside. Okay, and this is because of the internal force. Okay, so they're automatically, you don't have to do anything, it just automatically sucking the blood into the tube. Okay, that's because of the internal force. Okay. And why some of the bugs can stand on the water, right? They can stand on the water. This is also because of the internal force. And some of the case, why you have a waterproof coat. You have a waterproof coat. So when the water put on your coat, it will just flow away. It's not going to stand out that. It's because this guy, they're not going to bind in the water molecules. All of those coatings, they have the organic compounds. And remember, organic compounds is non-polar. And non-polar is not going to dissolve polar, right? We talk about like dissolve like, unlike dissolve cannot dissolve unlike. So if you have some organic, non-polar material on the outside of coats, the rain put on is not going to capture. So that's why there's a materials, a spray that you can buy from the Walmart. It just spray it on the surface, and then it will become a waterproof.
Yes, it's
That's where else it's well, it's not permanently, but but it take a while to like. Yeah. So a lot of people, if you raise the pets, dogs or cats, they prefer just to spray it on the sofa, and then so that easy to clean the hair. Okay, yeah. So this is one of the examples to dealing with the internet force. I think there's a lot of very interesting topics, but unfortunately, we don't have enough time to talk about that. What?
If you work at a bank. Yeah.
Yes. So IMF. Yes, you're talking. Yes, IMF, International Money Fund. Monetary Fund.
So yeah.
Okay. So the last topic. Okay, last topic I'm going to talk about is the last topic is called phase diagram. It's a phase diagram. This is the last topic that we're going to talk for the whole semester. It's called the phase diagram. So remember, phase, this phase here we talk about is a 3 different phase: solid, liquid, and gas. Okay, solid, liquid, and gas. So generally, solid, liquid, and gas, those are 3 different phases can be interchangeable by changing pressure and temperature. And we already learned you can change the temperature to change the phase from solid, liquid, and the gas. That makes sense, right? But you probably don't know, if you're changing the pressure, you can also change the phase.
Oh, deformation. It's like sticking straight.
Well, this is still a changing phase. I'm talking about pressure. For example, if you have a gas phases, and by the way, do you know how we making some of the gas, clean gas? It's called a air blower.
Like
The can air, right? If you do that, actually is a liquid inside. Okay, that's because this guy actually inside is a liquid air, but it's very high pressure to stand inside. So that's why if you have a pressure, then you can press the gas phase to a liquid phase. If you increase the pressure, you can make this from gas to the liquid. You can think about just gas molecule. The pressure is kind of like you're pushing the gas molecule closer to each other, right? If it's close to each other, then they become a liquid. That makes sense, right? Yeah, as long as you have enough pressure, then it will eventually become a liquid. Or if you have an even higher pressure, you can make it as a solid. Okay, that's gonna be nuts. Yes. Okay. Yeah. And this definitely is not a sustainable for a long time. Okay. There's no way. But generally, you can do it. That makes sense, right? Yeah. So, so that's why the phase diagram actually is the diagram that containing two parts. The x-axis is the temperature, and the y-axis is the pressure. Okay, so generally, based on this diagram, we divide this diagram into three parts. And remember, three parts: solid, liquid, and gas. Okay, then generally this is usually how the diagram looks like. Usually, this is what the diagram looks like. And on the left side, this is a solid phase, which is over here. Right side is a gas phase. Liquid is right in the middle. And the liquid is a really, really small part. Okay, so this area is a liquid. So what that means? You see, if you have a certain pressure, shows up here. I can give you one example for the water phase diagram. That's okay. Okay, so now you can see this is the phase diagram for water. Okay, this is a phase diagram for water. So now this is a pressure, which means at the room temperature at 1 atmosphere, this dots the zero. This dots means at 1 atmosphere and 0 Celsius. Okay, at 1 atmosphere and 0 Celsius. And this is the boundary between solid phase, liquid, and this is a gas. Okay, so this, if the dots is on the right on the boundary, then that means this is the transition between solid and liquid. You see, this is a solid phase. This area is a liquid phase, which means it doesn't matter which dots is in this, is or the liquid phase. In other words, if you have one of the temperature, the pressure, and represent a certain temperature over here, that's still a liquid. If you have if you have a low temperature, but if you have a really high pressure, it still become a liquid for a water. And if you shows over here, if you have a really high temperature, you have a really high temperature, and this temperature even higher than 100. Suppose it should be a gas phase, but if you have a very high temperature, there's still going to be a gas phase. Still going to be a liquid phase. Do you understand what the meaning on this part? Okay, yeah. So each of the dots shows on the graph actually is represent one of the temperature and the pressure. But I want you just to understand some of things. Okay, what is the meaning if there's a dots shows on the boundary? Okay, if you have a dots shows on the boundary, what does that mean? So shows on the boundary, then that means at this temperature and the pressure, this we're going to have a two phase shows, both liquid phase and a gas phase. This area is a gas phase and this area is a liquid. If there's a dot on the boundary, then that means at this temperature and this pressure, we're going to have a both phase shows, which is a liquid and a gas. Okay. If there's shows the dots shows on here, and that means at this temperature and this pressure, we're going to have a solid and a liquid phase. Maria, do you have any questions?
No, I'm sorry for the knowledge.
Any questions? Are you clear? And then what does this mean? This shows is called a triple point. Yeah, so that means at this temperature and the pressure, we're going to have a three different phase shows: liquid, gas, and solid. They are both shows of there. Are you clear? Okay, so this is generally the meaning of the phase diagram. So now, if I want you to talk about, since we have those phase diagram, if we have dot A, and this is dot B, and we have dot C, this is gas, and then we have dot D. So my question, so first of question, if I want to from C to A, what kind of parameter we need to change to get from C to A? From C to A, you're gonna increase the pressure, right? You're gonna increase pressure, maybe just increase a little bit temperature, but in most of cases, you need to increase the pressure to get from C to A. That makes sense, right? Then, what is the process? It is. We have a 5 different. What is the name of that phase change? Look at here. I didn't change the temperature. So if I just changing the pressure, we increase the pressure. What is it? This is condensation, right? From gas to liquid. From gas to liquid is a condensation. So you see, even you don't have to changing the temperature. You're just increase the pressure. We're going to make a, right? We just mentioned that you can give it the pressure and making a liquid from gas. Okay, yeah. Then from D to A, what is the name of this? From D to A, what is the name of this class? The phase change. This is a D is a solid, and this is a liquid. From D to A, that's a melting, right? So now I'm going to remind you the 6 different names of the phase change. From solid to liquid, this is a melting. From liquid to gas, that's a vaporization. And then from solid to gas, this is called a sublimation. From liquid to solids, this is called the freezing. From liquid, from gas to liquid, and this is called a condensation. And from gas to solids is called deposition. Okay, so we have a 6 phase change. So now what I want you to know, to read this is, if I give you several dots on the graph and telling you we have from one dot to another dot, can you tell what is the phase change? What is the name of the phase change, right? For example, If we talk about from A to B, what is the name? A to B, that's a vaporization, right? Because from liquid to the gas, vaporization. How about from D to B? D to B is a sublimation, okay? Yeah, D is a solid, B is a gas. From gas, then that's a sublimation, okay? From D to C, same sublimation, okay? Are you clear? Okay, yeah. And then just need to remember, okay, or for example, from A to C, what is the phase change? Okay, we know this is a this is a vaporization, right? What is the from A to C, what is the parameter you're gonna change? You just need to decrease the pressure. That's it. You see, once you decrease the pressure, then it becomes gas. Just like the reason, you see, the reason once you press the liquid air. What is it? The air cleaner? No, it's not air. I forgot what is the name for this air tank. Fresh. Okay, usually once you want to clean the computer, I mean there's a lot of dust, then you just ball the can air. So if you ball the can air and then you press it. Once you press the top tips, in general, it just open the pressure from air from the surrounding atmosphere and connect to the inside. So once it's open, then the pressure is suddenly released. Then they're going to become just from liquid to the gas. So the gas coming out. It makes sense, right? So generally, this is how it works. All right, so that's it for everything. Okay, that's it. This is for everything. Okay, do you have any questions? In the lab time, I will give you some of the practice. It says practice, and then I hope you're gonna work on it. Okay, yeah. So the better, the longer time staying here, the better. Okay, just work on those practice. Okay, yes.